But yeah. Okay, so our next talk comes from someone who needs very little introduction to the EML community, Dr. Petar Velickovic, staff research scientist at Google DeepMind, affiliate lecturer and an associate of Clark Hall, University of Cambridge. Petar's research focuses on graph neural networks and geometric deep learning, two areas that are transforming how we teach AI systems to understand structure, context, and relationships in data. His work has had a tremendous impact on how we model everything from molecules and biological networks to social systems and knowledge graphs. But beyond his groundbreaking research, Petar is also deeply passionate about AI education. He has been actively involved in designing educational programs that bring machine learning closer to young generations, from the Raspberry Pi Foundation's national AI curriculum in the UK to initiative in Serbia's mathematical gymnasium, where he helped shape advanced program for gifted students in math and computer science. He's also taught graph machine learning to students all around the world, from Chile to Australia, helping to make complex ideas accessible and inspiring the next wave of AI researchers. And as a fun part, Petar has been officially declared the tallest fellow of Clare Hall, University of Cambridge, standing proudly at 1.93 meters, which, as he likes to say, is fairly average by Montenegrin standards. Today, he'll take us through a fascinating journey into the world of graph neural networks, showing us how everything is connected. So please join me in welcoming Dr. Petar Velickovic with his talk, Everything is Connected, a modern tutorial on graph neural networks. Petar, the floor is yours.
Nothing like coming back to Montenegro to remind you of just how different distribution shifts can happen. When I'm in the UK, everybody tells me, oh, you're so tall. And here, I'm just average, right? Anyway, thank you so much once again, Tamara, for the fine introduction. And thank you all for joining me for this chat tutorial on graph machine learning. I realize I am currently the only thing standing between you and lunch, so I'm going to try to make it engaging. We have a little bit more time, so hopefully we'll have a nice discussion afterwards as well. As mentioned at the beginning, we will all have mentorship sessions during lunch, so please feel free to grab me and talk to me about anything you want to talk about after this talk is done. So, as the title implies, today we're going to be talking about graph machine learning, and specifically, we are going to be looking at how to build and leverage graph neural networks, and how to process graph structured data in a kind of consistent and reliable way. What I often like to say is, I'm going to come to you today to speak to you about graph representation learning, and I hope that by the end of my presentation you will think that we should all be doing graph representation learning, right? It's a tall order, but let's see how far we get together. This is actually a pretty fun artifact of using the Nano Banana model. I first gave earlier version of this tutorial in Chile earlier this year for Kipu, and I used Gemini after many attempts to create a map of Chile with like a graph superimposed on it. Now the technology has advanced so much, I can just say, give me this same thing but with the map of Montenegro, and it just gave it in one shot, which was pretty sweet. Okay, so since I've given you, I would say, a fairly tall order in I want to tell you that we should all be working on graphs, I feel like I should start by defending that position. I'm sure some of you in the audience, I see there's lots of people interested in graphs in the introduction channel on Slack, so great to see all of you. But I'm quite sure there's also many of you who are not convinced that we should be working only on graphs. So let's see why you should be thinking about graphs in your work. And maybe before we dive into the motivation, it might be good to just be all on the same page about what I mean when I say a graph. And this will serve two purposes. First of all, it will kind of make sure we all have a shared understanding of the term, because different people might interpret graph to be a very different thing. In fact, there's a notorious saying that like mathematicians completely hate graphs because there's 10 different ways to define them, and how you choose to define them changes their properties completely sometimes. So yeah, we're all going to be hopefully on the same page on what I mean when I say a graph. And in the process, we will also discover some interesting, exciting, and emerging applications, which will hopefully motivate why you should study data on graphs. So when When I say a graph, I think of a structure like this, right? So collection of entities, and they are interconnected by certain pairwise relations, and we want to be able to formalize these objects and hopefully do some machine learning on top of them, right? So the key building blocks are, first of all, nodes. So the individual entities, depending on which literature you're reading, you might see these guys referred to as nodes, vertices, points, whatever. I'm going to refer to them as nodes, but they all really mean the same thing, okay? So here we have a particular node U, and that node belongs in a set of nodes V. As I said, we need to also have connections between them. We typically formalize these connections through the concept of an edge. So an edge tells you that a pair of nodes are connected, and you can express this as basically an ordered pair of two nodes, and that belongs in a set of edges E. And what is a graph? It's no more or less than just these two sets together, right? A graph is a set of nodes and a set of edges in its most basic form. Okay, so this looks like a fairly interesting generic structure. Certainly, it has a more non-trivial structure than, say, text or images. So what might we be able to do with this that we couldn't easily do with text or images? Well, first of all, I'm going to guide you through a few standard examples. This is one which maybe is not the first thing that would come to your mind, but if you start to study these models, it's probably the first example you will see. You can imagine these nodes as being different documents, academic papers, or something like this. So each node is like a document. And you can have a link between two documents if one of them cites the other. This is a very common practice in research, where one paper will typically have many tens or hundreds of citations. Or even if you want to study some encyclopedia, like Wikipedia. Each node can be an article on Wikipedia, and different articles might link to different articles. And you might be interested then in predicting various things about your documents. For example, what type of document it is, or if it's a paper, which part of machine learning does it belong to. This is not just a toy task. It is something that, if you knew how to do it well, would massively accelerate work that is today done by humans. For those of you who do science, you probably know about arXiv, the science repository. It might seem like a nice and seamless process, but it actually relies on hundreds of human moderators that skim every paper you submit to the arXiv and label, is the type you chose for this paper correct? Because very often people don't choose the correct type, or they will say their paper is AI to give the paper more hype, but it's actually not AI, or things like this. So currently this is all done by humans because the AI systems are not powerful enough to reliably replace the humans doing this. And it's tedious work. Like, it would be much better if humans weren't doing this. They could do more useful stuff otherwise. So yeah, this node classification problem, we have many existing huge data sets, up to hundreds of millions of nodes. If you make progress on this, you can make lives better for many, many people doing tedious work. Okay, here is an example that's a bit closer to home for me because I've had the honor and pleasure to personally work on it. You can imagine a road network as a graph, okay? So each node might be a segment of road, yeah? Each edge is, say, an intersection between two segments of road. And you might be interested to predict stuff around these segments of road. Now you're doing like a regression task rather than a classification task. You're predicting something like, say, if I decide to drive on this segment of road right now, how long will it take me? How many seconds or minutes or whatever, right? You can hopefully imagine how a system like this could be really valuable in predicting how long it takes you to get somewhere. And unlike the previous case, where we're not yet at the phase where these systems are actually deployed autonomously, in this case, I can tell you firsthand that they are because I co-developed one of them, yeah? I'm sure many of you use Google Maps in your day-to-day life. And even if you don't use it, you probably use it implicitly because many different services like food delivery apps, rideshare apps, rely on the Google Maps API to tell you how quickly your food is going to arrive, how quickly your car is going to arrive, and stuff like that. Obviously, very important information for our daily planning. And one of the features that Google Maps offers you is this very neat travel time prediction, which is the amount of minutes that it will take you to drive on a particular segment of road, which can then be used, among other things, to recommend you which road you should take, but also to allow you to plan your day a bit better. And This might seem obvious in hindsight because the road network is a complicated graph, but for many years, Google's production system for doing this did not take into account the graph structure at all. It just looked at historical data, like around this time, this road segment, the speeds were roughly like this. Let's just use that and integrate the results together. This completely ignores things like unexpected traffic jams, the afternoon spitz, and things like this, right? Things that actually make a big impact on the travel time, but you can't predict them if you just observe historical data right now, yeah? But if you look at the graph topology and you see that there is a clutch happening somewhere, the graph neural network can help you spread that information across and figure out that maybe not right now, but in 10 minutes, you're gonna have a hard time, right? And I know that this weekend we have the marathon in Podgorica, which is probably going to cause some of these issues as well, unexpectedly rerouting traffic in weird ways, right? Especially for us who need to go to the airport tomorrow. But anyways, when we deployed the system, it might seem obvious in hindsight, but when we built the system and deployed it, in some cities in the world, we reduced the negative outcomes, which is like the system being wrong by more than 10 minutes or something, by up to 50% relative improvement. So more than half of the cases that the model got wrong before we included the graphs now are solved in a reasonable way. And you can see, obviously, when we launched the system, these were the relative gains in different parts of the world. Obviously, certain cities, the gains will be much higher because the traffic in those cities is much less easy to easily predict. So places like Sydney, Taichung, also some cities in India, those tend to be really tricky to predict travel time on. In some more streamlined cities, it's a bit easier, so you don't get as much improvement from the graph. But this system is alive and running in production right now, everywhere in the world, including Podgorica. So when you use Google Maps to plan your morning commute or anything like this, you're using a system that my team co-developed. So if you have any complaints, I'm very happy to talk to you about this. But you know, it's not going to be perfect, but the data clearly shows it improved stuff. And it's used by billions of people every single day. So you're interacting with a graph neural network without necessarily even knowing you're doing that. Okay, so that was node regression, another very standard task that you can do in this space. You can also, so we talked about node tasks, like predicting things about the individual items, but you can also predict stuff about the entire graph. Here is another very standard example, very relevant for medical AI and biology, which I'm sure Natasha will tell you a lot more about than I can in the time I have. But basically, here, now your nodes become atoms, like building blocks of a molecule, and your edges are the chemical bonds connecting the different parts of molecules together. So now, you're not that much interested in predicting stuff about the atoms, unless you want to do physics models, but here we care more about analyzing the molecule itself. So you're predicting things on the level of the entire graph. And when you have small molecules like this can be like paracetamol or something like this, you might be interested to predict something about its clinical activity. Will it be potentially a potent drug for a rare disease? Or how toxic is it? Does it have any negative side effects if you take it? How soluble in water is it? All kinds of things that are really important for the development of new pharmaceuticals. And I need to stress once again, just like in the case of the road networks, this is not a toy example. This has already been used to discover very influential molecules, okay? And I should also stress, it was actually one of the earliest drivers of graph machine learning. This is the cool thing about computational chemistry, is that chemists don't really wait for machine learning to catch up to their needs. They realized they were looking at graphs already in the 90s. Which led basically to computational chemists proposing graph neural networks years before the term graph neural network ever existed. So in the mid-90s, you have these papers from Dmitry Kireev, Igor Baskin, and even more later in 2005 from Merkwirth and Lengauer, basically realizing we have data that is molecular. This data looks like a graph. We need to build a learning system on top of this. And they ended up proposing some equations which look very, very similar to the GNNs we use today. So as one computational chemist friend told me once, chemistry disrupts machine learning, not the other way around, okay? But here is, you know, in recent years, it has really started to have a resurgence. I was showing you, you know, results from the 90s or early 2000s, but the deep learning boom did not stop these progresses in computational chemistry. And here are just a couple of references if you're interested in this particular space and you'd like to learn more about how the field evolved. From the very influential work of David Duvenoff for convolutional networks and graphs for learning molecular fingerprints, all the way to Justin Gilmer's paper on using message passing models to model quantum chemistry. So to like try to approximate really expensive density function theory experiments using very, very fast graph machine learning systems. So papers like these really brought a resurgence to this field in recent years. And these were actually the real results that I wanted to share with you, is that actually they have been used, like the systems like the ones I showed you, have been used to discover new influential molecules already. And this is documented research in top-tier biological journals like Cell, Nature Chemical Biology, and so on. Specifically, I want you to focus on these two molecules. The first paper discovered a molecule called halicin. The second paper discovered a molecule called abaucin. In both cases, it was basically the pipeline I showed you, a graph machine learning model looking at nodes and edges, predicting chemical activity. You train it on molecules for which you know whether they're a drug for this disease, and then you just test them on molecules where you don't know. And sometimes, the model will give you a probability. Sometimes the probability of being a drug is super high. So even though you wouldn't expect this to be a drug, you still send it to chemists, and maybe chemists find something interesting sitting in that pile of high probability compounds. And in this case, this is exactly what happened in these two papers. Halicin is a particularly interesting one. I don't know if we have any chemists in the audience, but basically, this compound was identified as a really powerful antibiotic, so a molecule to fight bacteria. But show this to any computational chemist and they will say, what the hell? This does not look like an antibiotic. This does not have the structure that most typical antibiotics will have. In fact, the reason why halicin was even in the data set is because at the same time they were testing if it could be a drug for diabetes, which is a completely different thing, right? So it turns out that it's precisely because it has this super unusual structure that halicin is not only a potent antibiotic, but it's also having a completely different mechanism of action to the antibiotics we're normally used to. And as a result, it actually works really well even against the antibiotic-resistant bacteria strains that have over the decades learned to, overfit to the drugs we pipe into our systems all the time and have learned to kind of counteract them. So here, by using the graph neural network, we were able to explore a fraction of chemical space where chemists didn't even expect to look for antibiotics. And these are molecules, as I said, that have already been found in specific studies in the drug repurposing hubs. Okay, it goes beyond just discovering small molecules in drug discovery. These types of graph models have also been applied in material science. One influential paper from DeepMind a couple years back, the GNOME paper, used such a pipeline to discover millions of new possible materials. And this one, which I find particularly cute, another work from our colleagues at Google, which was actually published in Science, one of the top journals, used this graph neural network system to predict smells from molecules. So predicting what kind of smell will a molecule have. And as far as I'm aware, they have been able to, spin off some of this technology and try to do something that will potentially revolutionize the perfume industry, right? Because you're going to be able to foreshadow what kind of smell will a molecule have before needing to mass produce it. Okay, so hopefully, this is, I think, a part where, in my opinion, the most influential and the most important applications of graph machine learning are, but we've only started. I'm going to show you several more, but hopefully this is already quite convincing, what you've seen so far. Okay, so we talked about predicting stuff on the nodes. We've talked about predicting stuff on the level of the whole graph, but we haven't yet talked about the edges. And actually, if you're on the internet, you're very likely interacting with a graph neural network, and precisely you're interacting with a system like this, a system that predicts links. So you can either predict certain properties about edges or even predict whether edges exist or not in the actual structure. And that's why traditionally we call such models link predictors, even though they don't necessarily have to predict the existence of links. This is one very common way to do this. And a very common setting, you find this in our social networks. So here, your nodes can be different people in a social network. Your edges can be known friendship links or other kinds of connections between the users. And your link predictor can, suggest who should be your friend next based on all of the data that you have. Or, it doesn't just have to be friendship. It can also be kind of a more heterogeneous structure, which has both people and items or products. So imagine your nodes here are either people or different products, and the edges will tell you which people have purchased which products are often purchased together, stuff like that. And here a link predictor can be, recommendations on what are the next thing you should buy based on your previous purchasing history and the overall graph of shopping, right? And as I said, if you're on the internet, you are very, very likely interacting with precisely this type of GNN. And what I'm going to show you now is like a handful of examples, but those are only the examples of companies that went public telling you that they're using this technology in their systems. There's probably way more cases where, the company just didn't release this IP. So one example is Uber Eats, a very popular food delivery service. It actually has this view where it shows you what are the restaurants you can order from, what are the dishes you should order from those restaurants. And it's not random. It's not sorted in like an arbitrary way. It actually uses, they have a blog post describing how they use graph machine learning to sort in what order they will recommend you these things based on your previous food purchasing history. Airbnb, I'm sure some of us have used Airbnb at least once or twice. Airbnb also has a very nice blog post showing how they use graph machine learning to recommend you where you should stay based on your preferences and previous experiences of previous people. This one example I also really like to show. Amazon, the world's biggest online marketplace, has a very nice P-companion paper where they show how to use graph machine learning not only to recommend which products you should buy, but to recommend it in a way that is complementary to what you've already done. So if you've purchased a Novak Djokovic racket, yeah, certainly the model should not recommend you to buy other rackets, because not only do you not need more than one racket, they're also all clearly inferior to Djokovic's racket, right? That's obvious, right? Then, okay, you might then say, okay, you might want some tennis balls with that. But then again, if the system only recommends a bunch of tennis ball products, that's not useful either, because you're only building part of your tennis package, right? So the best possible recommendation once you buy a racket will tell you, you might want some balls for that. You might also want a carry case. You might want a headband, complementary recommendations, and also not inferior recommendations, as I said. Okay, I don't know if any of you use Pinterest. Pinterest is a very popular impression sharing platform, very popular with architects, interior decorators, and so on. We actually used Pinterest very actively when we were redecorating our home. The reason why I mentioned Pinterest here particularly is because it is actually the first documented top-tier paper published using graph neural networks on billion-node graphs. So Pinterest actually used these models to recommend which pieces of content you should look at next based on the things you've seen before. And they're kind of influential because they were the first group to really go public with all the details of what they were doing. I'm sure some of you use Spotify. I use Spotify pretty extensively. They recently published a very cool paper. They have a very big graph machine learning team, and they've shown in their work how they're using these models to recommend which audiobooks and podcasts you should listen to next based on the content of what you've listened to before, and also based on what other users of Spotify also like to listen together. I am certain many of you use LinkedIn because already many of you have added me on LinkedIn. Recently, there was a really cool paper from the team at LinkedIn showing how they use graph neural networks to recommend which jobs you should apply to next, which people you should connect with, and all sorts of things. Yeah. And also Snapchat. I am not young enough to use Snapchat, unfortunately, but from what I know, basically they also rely heavily on graph machine learning, and they have a published paper. They're a very active research group using these large-scale models to recommend content you should look at on Snapchat. So, I mean, there's many more examples. I only listed to you the publicly available ones. So I hope I've convinced you that if you're on the internet, you're very likely querying a model like this at some point during your day. Yeah? So that's one way of looking at it, right? So it might be useful to work on this data because it's very influential, because kind of steering these models will change the way content is served to users, and that might be a really beneficial thing depending on the application. But going back to maybe a more machine learning or kind of theoretical grounding on why graphs are so versatile, it's also pretty meaningful to note that the more standard modalities of data, like text and images, are also very neatly representable as graphs. So basically, if you decide to work on graphs, you can still work on images. They're secretly graphs. So here is an example of a severely downsampled 4 from the MNIST dataset. I made it 8 by 8, so I can exactly map it to a graph in one slide. And here you can see, you can exactly interpret this collection of pixels as a graph structure where each node is a pixel, and each pixel has its 8 immediate neighboring pixels. If you describe a graph neural network model over such an input, and we'll talk about this later, you are effectively specifying a convolutional neural network over that same input. Yeah? But the cool thing about that is you don't have to stop at images, right? We just had this amazing talk about Earth observations, and as you will probably know, if you want to model stuff on the entire surface of the Earth, representing it as a flat plane is no longer necessarily a good idea. Because imagine you take the usual Mercator projection, right? The way maps are typically rendered. I'm sure you know that Greenland is not actually as big as it looks on those maps, and Australia is not as small as it looks on those maps, right? Africa also much bigger than it looks on these maps. So the closer you get to the poles, the bigger things get and the more curved things get. So good luck reliably using a convolutional neural network to predict stuff on the surface of the Earth. And there are super meaningful stuff you can predict on the surface of the Earth, which we'll talk about in a bit. This is one maybe unexpected example. In astrophysics, we often care about predicting stuff on the surface of the Earth because a lot of our telescopes receive information the way it's reflected on the surface of the Earth. So we really want to understand that kind of data if we want to understand the universe. Yeah? And graphs, as you might expect, are a very natural way to model that because now you're not limiting yourselves to a flat plane. You can have a mesh which covers different parts of the Earth reliably and consistently. And then you can use this to simulate all sorts of effects on the surface of the Earth in a way that doesn't depend on the projection choice or the curvature or things like that. One very common example is predicting the weather, which is a really important thing to do, and is something that my colleagues at DeepMind have worked on quite intensely over the past years. This is a landmark paper called GraphCast that was on the cover of Science a couple of years ago. And it showed that if you have a graph model like this and you have different nodes representing parts of the Earth and you model atmospheric conditions like pressures, temperatures, and stuff like that, you can actually do medium range weather forecasting more accurately than any other system out there. And this is not, it's already deployed in some of Google's products that will tell you more accurately when it's going to rain, what the temperatures will be. But I think a far more impactful outcome of a system like that is that it helps us predict extreme weather events much more accurately. And as we have global warming and climate change, such events are going to be more and more common, So hurricanes, things like this, it would be really useful if we knew earlier where those hurricanes are going to hit more exactly so that we know how to prepare the evacuation measures in advance. And here you can see actually the predictions of the model. The blue are the possible rollouts of the model's predictions, and the red is the actual trajectory that the hurricane took. And you can see already 7 days in advance, this model can sort of predict roughly what way the hurricane is going to go. And as you get closer and closer to impact, it gets more and more accurate. So this is not only a research paper, the outputs of this are already used to actively train hurricanes. In fact, the recent Hurricane Melissa was tracked using a system derived from this, and it has been able to quite accurately predict where that hurricane was going to land. So it's very out of distribution, very current. I wasn't involved on that paper, but I was involved in this one. It actually came out a couple of days ago. I'm quite happy I got the chance to share it with you today. We have also used these graph models on the surface of the Earth to model the distribution of species of animals. This is extremely important, as Sanya already mentioned in her talk briefly, that because our species, our ecosystems are collapsing. We are losing more and more species on a daily level. And really, how good we are at preserving them relies on the measures that are taken to protect certain parts of land, right? But in order to know which parts of land to protect, you need to know where is the reliable habitat for this species. And as you might expect, it's not sometimes easy to track, a single animal, let alone a huge population of animals where they might be or where they might possibly be. the data simply is not there yet, and it's not easy to collect. But with using these graph machine learning models, we've shown that you can effectively take citizen science data and from that create very plausible maps which basically match or sometimes even exceed the predictions done by state-of-the-art statistical models used by the United Nations. So how this works, specifically the maps I show you here are for this very cute species that lives in Australia, the southern greater glider. I highly recommend you check out some videos on them. They are the cutest mammal imaginable, but they're super endangered as well. So we really need to work hard to protect them. And what we have as data points are these bunch of points of just very keen explorers who go out in the world and they take pictures of these cute mammals. And so we have a map of different places where they have been spotted. So it's just a bunch of points on the surface of the Earth. And then we use a graph neural network where our nodes are the different animal species we're modeling and the different locations on the surface of the Earth. And we just make an edge if species I was spotted in location J. And then we just ask the model to predict those links in a typical link prediction objective. And we're able to get really rich maps. So these were the data points we had access to for the southern greater glider. These were the outputs we got. Notice how not only it fit well around the points that we had, it also forecast that they will be located in parts of Tasmania, which was not in the data, but they do indeed exist in Tasmania as well. And also it extrapolated to the north in regions that have similar climate, where actually greater gliders have been spotted as well. Yeah? So just from citizen science, pointwise data, and the power of graph learning, we can do things like this. And these maps have already been publicly released for 23 species of Australian mammals on the UN biodiversity website. So if you're interested, you can play with these maps and the data we've created already. Okay, are there any football fans in the audience? I hope there's at least some football fans in the audience. Here's another maybe unexpected application of graph machine learning that we've worked on for a period of 5 years together with Liverpool Football Club. It's, I think, the first time a sports analytics paper was published in Nature Communications. Basically, using graph machine learning methods on a graph formed of different players in the game of football to predict certain outcomes. Who's going to receive the ball, who's going to score a goal, but most excitingly, how should I change the positions and orientations of my players to maximize the chances of either scoring a goal or not conceding a goal, right? And these adjustments that were created by our graph system, which explicitly models the relationships between human players, was seen, first of all, as equally powerful as the top coaches and experts at Liverpool. So the system predicts who will receive the ball with roughly the same accuracy as the top coaches at Liverpool. And also the adjustments produced by the system have generally been judged in 90% of the cases as more useful and more useful for the defending team than the actual plays that took place in the Premier League. So we don't actually know what Liverpool did with this technology. We have published the paper together and helped them integrate it. What they've done with it, we don't know, but they have won the Premier League last year, so draw your own conclusions. Okay, now, I gave you a bunch of specific examples, maybe some you were not expecting, but I hope there is a sense of how general modeling things with a graph can be. Yeah? And I would like to go even one level higher than this and say that if we want to build kind of a generally intelligent system, we might benefit from kind of graph structured processing. So imagine a case where your nodes are now memories or concepts or things you've understood throughout your experience. And the edges are connections between those concepts that help you quickly conclude new things or draw new pieces of knowledge, right? And then imagine you have like a graph classifier which looks at all of your experiences, the links between them, and decides how to act in the environment to gather new knowledge, to get optimal outcomes, things like that. I think I've just described the generally intelligent system to you. So based on kind of a concept like this, I would say if you want to build a generally intelligent agent, there's going to have to be some graphs in there, okay? Now, you might think, hang on, this is in contradiction with the fact that modern LLMs use transformer models and transformers are not GNNs. I will tell you in a few slides' time that actually that's wrong. The building block of modern large language models is actually secretly a graph model. Okay. So hopefully, now that we've done all of these examples together, we have a more clear answer to the question, why graphs? And hopefully you've gotten some interesting new applications of interest that you might want to talk to me about over the lunch break. Okay, so now that we have that, let's ask ourselves, like, now that we kind of agree that it's a good idea to study data that lives on graphs, let's talk about how to do it. So what's in a graph neural network? Okay, so going back to our abstract picture, this is our graph, we have our nodes, we have our edges, things like that. But this is a very abstractified kind of computer science style picture. And as was elucidated in Razvan's lecture, you can't just feed a structure like this into a computer or a graphics card and expect things to come out very smoothly. Modern deep learning architectures require matrices, very densely packed matrices. So what you actually show to a system, to an AI system, is something that looks a bit more like this. So you don't show it like this collection of nodes and edges the way you would in a typical computer science, C++ setting. But you show it these two matrices. The first one we call the node feature matrix, X, which has number of rows equal to the number of nodes and number of columns equal to the number of features you have in each node. So really each row of this matrix tells you the embedding of a particular node. And here I went A, B, C, D, U, V. I've labeled all the nodes, so we have a nice correspondence to the original picture. And you also need a way to express the edges. And to do that, one very standard way, which plays very nicely with matrix operations, is the adjacency matrix. So here it's just this binary matrix where you either have a 0 or a 1, and on a particular position it tells you whether this node is connected to this other node, right? So it's the shape of that matrix is nodes by nodes. And of course, as we discussed in the case of, say, chemistry, you can put extra features on the edges, like what bond type it is it in a ring, or things like that. But we can actually assume there's no features in the edges, they're just 0, 1, and all the math will still be the same. Even if we had features in the edges, it will just be a lot more tedious. And I don't like tedious stuff, so I'm just going to assume for the rest of this talk that there are no features in the edges. Okay? We can easily generalize that to the case where there are. Okay, now notice one thing that you might find interesting here is I've ordered my nodes in some way, A, B, C, D, U, V. I mean, that's like alphabetical order, but did I have to do it that way, right? Do we have any notion of ordering in a graph? We typically don't. So the very kind of action of putting nodes in a matrix in this order is actually not good. And I would like my system to not depend on me making bad choices like that. So effectively, if I choose to change the order in which these nodes are presented in the matrices, that shouldn't change the answers I get. Or at least it should change them very predictably. So what I'm trying to say here is if I've built a graph neural network, this function f, which takes my graph, specified as I just told you, and outputs some classification label or a regression label, like say if this graph is a molecule, predicts whether it will be a potent drug. What I want is, if I choose a different order, right? If I choose to do U, V, B, A, C, D, whatever, right? And appropriately change the order of my edge matrix as well, I would like the model to give me the same answer in those two cases, right? Because otherwise something is broken, right? And actually, this is a very fundamental property that underpins all graph machine learning models. It also underpins transformers, although it's a bit more secret there, is this idea of permutation invariance, right? Because what is the operation that changes the order of things? It's a permutation. And basically what we're trying to say is for something to be a valid graph model, it must give the same answer for all possible permutations of the rows of the node matrix and rows and columns of the adjacency matrix. And we can express this as multiplication with a permutation matrix P. Every permutation specifies a particular permutation matrix such that when you multiply it with your data, it just rearranges the rows and does nothing else. You can do a similar thing to your adjacency. You just have to rearrange both the rows and the columns, and that's why you get PAP transposed. Yeah? Now, this works really well if I'm just doing molecule classification. Like I want for one graph, one output. But what if I want to predict stuff in the nodes, right? So I have now predictions for every one of these guys. Obviously, if I permute my nodes, I should expect different answers now, but they should be different in a very predictable way. In fact, they should be permuted in the same way, right? So what I want in this case is actually, so here I have, my original node ordering. Here I have a different node ordering. And I want the outcome of that to be the same as the outcome of this, but permuted in the same way, right? So I want to reconstruct this ABCDUV permutation here. So I basically have this extra multiplication with P in the condition that I'm doing, and that's the idea. So now, if you want outputs in each node, those outputs must change, but they must change equivariantly, so according to the permutation, okay? And now I'm using a capital F to denote my neural network, just to denote that the output of it will be a matrix rather than a single output, right? Okay, and one way in which we can satisfy this condition, because I've told you what the condition is, I haven't told you how to satisfy it, is just have a local layer that acts on every node separately and its neighborhood separately. So specifically, rather than expressing this big function f, you can instead specify a much more local function, little f, that acts just on one node and on all of its neighboring features and ignores everything else. And then you can just run this function in parallel everywhere. And it's easy to prove, and I invite you to try to prove it if it's not obvious, that if you do things in this way, you will get permutation equivariance for free, okay? So long as this local function f is invariant to the order of the neighbors, right? So as long as it doesn't depend in what order I present you the neighbors, the final outcome will be the same. And I would also argue that this might be the only way to satisfy permutation equivariance, but opinions are divided, so I don't want to present this to you as a definitive fact. Now, I've shown you a lot of math and a lot of tensors, but in reality, what I've shown you was this. This is really what's happening. So a way a graph neural network works is it looks at the embeddings of a node, it looks at the embeddings of all of its neighbors, and based on that collection, predicts some updated embeddings for each node. And you do this in parallel for all the neighborhoods. You stack more layers, as is typical deep learning fashion, and you predict stuff that comes out at the end. You might find it interesting that I've put a double curly bracket here. Normally sets are denoted with a single curly bracket. That is because this is a multi-set rather than a set. That means that I might have multiple neighbors with the same features, and I want to count them separately. I don't want the repetitions to be treated the same. Okay, so once you have a local function like this, we'll talk more about how to implement it. For now, we just know there is a local function acting on a node and its neighborhood. How can we then use this to, I would say, solve 99.9% of all of deep learning, including all of the examples I've showed you in the beginning of the talk? You take your graph structure with your input features and your adjacency matrix. You use the GNN that we just described, which looks at the local neighborhood of a particular node, to move us from this input space to the latent space. So it's some updated high-dimensional features for each node. Typically, this model leaves the graph structure alone, so the adjacency stays the same. We will talk later why that is a bad idea, but for now, let's assume we're doing that. And once we have these node embeddings, we can do all those different tasks that I talked about with them. So if you want to predict the time of travel in a road network or the category of a document, you just classify each of these nodes separately, just like you would in a typical deep learning system, right? Just logistic regression or something like this applied to everything. If you want to classify an entire graph, like predicting molecular activity, then you now need to classify all the nodes together, but you need to do this in a way that doesn't depend on the order. Remember, permutation invariance. And one typical way to do this is to just take all of your embeddings and combine them together using some aggregation function, which I'm going to use as O+. And this can be any function which doesn't depend on the order of its operands. So sum, maximum, average, anything you can think of which doesn't depend on the order is totally fine. And then once you aggregate all those nodes, you predict the output. And if you want to predict new links in a social network, or which players in football have synergies together, or where will a species be next observed, you can do link prediction. And it's a similar setup to node classification, only now your predictor looks at both the features of the nodes and maybe any features of the edges that you might have, right? And this picture here, I would say 99.9% of all of deep learning we do today is explained in this one picture. So everything is like a special case of one of the possible pathways here. The reason why is graphs are insanely general and computers can't represent continuous data, okay? So you have to discretize your data at some point, and at that point you have nodes and edges. Like the memory cells in the RAM memory are nodes in a graph, if you want to go that deep. Of course, this is absurdly general, but just saying that it's a framework that you can use for a lot of things. Okay. Now, I should just stress that I've talked about everything in a very graph-centric way, and I haven't assumed any particular structure to the nodes, which is why the permutation symmetry was appropriate. But it's really just a special case of a much bigger picture. In general, you can choose that your data lives on a particular space, and you can say it's resistant to a particular symmetry. We talked about permutations, but there could be other symmetries as well. And actually, by choosing the domain in the symmetry group and solving the mathematical constraints, you might end up with many standard machine learning models, okay? So for GNNs, we talked about the case where our data lives on a graph and our symmetries are permutations. But you can get convolutional networks if you assume your data lives on a grid lattice and your symmetries are translations, so shifts in the image. You can get spherical models by modeling rotations on a sphere. And you can even get transformers by permutations. Interesting. Okay, we'll talk about that a bit later. This is a very rich picture, which you can use to reason about many different deep learning architectures. And it's kind of formalized in our geometric deep learning blueprint that I worked on over the past years with Michael Bronstein, Jean Bruna, and Taco Cohen. If you want to learn more about this perspective, I won't have more time to talk to you about it today. But if you want to learn more about it, you can go to geometricdeeplearning.com. We have, shorter versions of our book. We're currently writing our book chapters. We have lecture notes. We have keynotes, blogs, code. Whatever you need, we probably have it. Whatever your favorite modality of learning is, we have it. Please check it out if you're interested. And I'd love to talk to you more about it later if you want. Okay. Now, constraints aside. So what we've talked about so far is we started from the idea of we would like to learn something useful on a graph, but we've only said the way to do that is to have this local function that looks at a node and all its neighbors. But I haven't yet told you what that function is. Now we're going to talk about that. So how to actually implement graph neural networks in code. And I should stress that research on how to do this is exceptionally rich. To this day, I still think it's one of the most active areas of AI research. And it started remarkably early, partly due to the help of Jürgen Schmidhuber, who always likes to seek out the earliest possible citations for something. People have been studying graph machine learning models as early as 1993, the year when I was born. Wow, crazy. This was a NeurIPS paper from Alessandro Sperduti, who is to this day a professor in Italy working on these techniques. And he looked at techniques using machine learning to encode directed acyclic graphs, which are a very specific case of graphs, but they are applicable in many general situations. And then sometime in 1995, Andreas Kühler and Christoph Goller also worked on backpropagating through structure, where they learned representations of various trees. So already in 93 and 95, there were some interesting works trying to define such functions. The name graph neural network actually took much longer to formalize. The first such use of the term arose in this paper from Marco Gori, Franco Scarselli, and Alessio Micheli, which was published, I think, in the first iteration in 2005, and then the full journal version came out in 2007. One interesting thing to note, though, is that these original GNNs were particularly complex structures. They needed a very special form of backpropagation to train, and they were more recurrent than convolutional. So they're actually not as similar to the modern day applications of GNNs. A much closer variant was done in Alessio Micheli's lab, the neural network for graphs model, which actually went on a less recurrent and more convolutional approach. And the two papers were basically kind of in parallel, but people tend to cite more the first one because of the name GNN, which has stuck more than the second one. And I should also stress, if you're interested in graphs and you ever have a chance to visit Italy, I warmly recommend stopping by Siena or Pisa. Specifically in Siena is where Marco's research group is, and they are still doing to this day top-notch graph machine learning research. I've had the great pleasure of visiting this group twice. One very fun anecdote, though, is that the computer science department in the University of Siena is located in what used to be a psychiatric hospital. So you go in front of the building and it says Ospedale Psichiatrico. It's very surreal and sort of accurate for computer scientists. Anyway, okay. So now that was the history. Now let's talk about how it's been done in the last 6 or 7 years. So graph neural networks had a massive resurgence from those early days back in 2017, and people have really tried to keep it simple. Like the most resurging models have went for a very simple way to look at a node's neighborhood and update its features. So here I've visualized a node and its immediate neighborhood, and we're going to learn how to update the features of that node based on the neighborhood. So one very standard way in which you can do this is you go over all of your neighbors. You take the neighbor features, you map them to some message space using a learnable weight matrix, so typical linear layer. Then you sum up all of them, their contributions, using a permutation invariant aggregator like sum, and then you just average them. So you divide by the total number of neighbors, which is the degree of node U. Yeah? And then you apply your favorite activation function. You can use the ReLU that Razvan talked about. You can use sigmoids. You can use more fancy functions. But this is a typical way in which the basic graph convolutional networks are applied today. Just basically take averages of everything coming to you. Yeah? The only learnable parameters here is the weight matrix W, okay? And you can learn this through usual backpropagation. But generally, the dynamics you get from a simple average are not that interesting. You actually get more interesting dynamics if you symmetrically normalize. So you divide by the square root of the degree of the first node and the neighbor. So this basically weighs the contribution depending on how much of a popular star you are in your social network. In a way, kind of giving more weight to the neighbors that are more influential, if that makes sense. And this particular layer is currently the top cited graph neural network paper there is. I think it now has 50,000 citations or something like this. The GCN from Thomas Kipp and Max Welling, published at ICLR 2017. I should stress that this layer, the implementation of it is quite simple, but it actually takes inspiration from a long line of spectrally inspired GNNs. So people initially try to define GNNs by looking at the frequency domain of the graphs. So, papers like graph Fourier transforms, Chebyshev networks, Monet, and even GraphStage to some extent, all relied on this spectral view of the graphs. What Kipp and Welling's paper did basically was to show that you can just use a very simple order 1 approximation to all of that Fourier stuff, and it works much better than all the Fourier stuff in practice because you have big data, and it's just easier to gain access to that data when you don't have to compute spectral stuff. But there is a long line of inspiration that led to this work. It didn't just magically appear in 2017 without any context. However, such a simple model is not going to be without weaknesses. And remember, I showed you before that nice picture of an MNIST4. Graphs allow you to look at images as a special case. And ideally, if you have a powerful graph neural network, it should be able to do everything that a convolution neural network could do, right? So a convolution neural net just takes, say, a small 3x3 matrix and slides it across the image, computing features as it goes. However, if you naively do this kind of averaging by degree, you actually cannot implement arbitrary convolutions. And this was a very famous critique of graph convnets by Ferenc Huszár, which actually led to a bit of a doubtful period into are these models really capable of doing all of these different things. Because basically, if you apply this on the image graph, as I showed it to you before, you can see that if you look at the different degree distributions, all of your immediate neighbors have to be treated the same, actually. So the weighings that you get, the coefficients you get for the different nodes, have to have this radial structure. So everything which is a certain distance away must have the same overall weight. So you can only do filters that look like circles. And that's obviously not everything you can do to process an image, right? Now, obviously, we managed to circumvent this issue. That's why we're still talking about GNNs today. But the main remark is that, in this equation, the only thing that made us decide the coefficient was the degree, the shape of the graph locally. But we also have access to other stuff which we could use to determine the coefficient of interaction. Can anybody tell me what other stuff could we use to figure out the coefficient of interaction? Sorry? The label? Or is that what you said? You could use global connections, but like in this equation, do we have anything else we can use other than du and dv? Yes? Yes, so the x's, right? We have properties of the nodes, and we can literally derive the interactions from those node features. And when we generally have a function that takes a pair of vectors and outputs a coefficient of interaction, we tend to call these things attention mechanisms. That's just the way they're called nowadays. So any kind of, we basically replace the 1 divided by square root of du dv by just a function that takes the two sets of node features and predicts a scalar. And that now tells me how much does node u care about node v in this graph in a way that depends on the data, not only on the structure. And this is what led us to graph attention networks. This, I guess, in the research world is one of my claims to fame. It's a paper we published at ICLR 2018. And it was one of the earliest attempts to try to plug attention mechanisms like this on top of graph data. I should stress that how you exactly implement this function alpha is very much task dependent. What we used in the original paper is actually super, super weak because the graph data sets at the time were really, really bad. Super easy to overfit. Very easy to run though, but super easy to overfit. So we used like a linear function for alpha, which was very, very simple. Many papers after our paper then debunked our choice and said this is a really bad choice. GATV2 is a really good choice, a really good paper to read in that regard. But basically, you know, we weren't unknowingly making a bad choice. We made a bad choice because the data was bad, okay? So these models now finally allow us to have an image model in the sense that different pixels on the image can now interact based on their properties and even based on their positions, and based on that have a different feature map for different pixels and not just circular maps that we talked about before. But can we do something even more generic than just a weighted sum, which is what we're doing here? Like we're still just taking neighbor features and doing a weighted sum of all of them. Turns out we can. This leads us to the message passing neural network, which is arguably one of the most general functions in all of deep learning. What we've done here compared to, so what we've done in this equation is we're aggregating something that comes only from the neighbor. But here, actually the neighbor and the node collaborate to compute a vector. Okay, previously they collaborated to compute a scalar. Now they're computing an entire message vector, and that then gets sent across into node B's mailbox to be aggregated. So previously we had a function here that only depended on V. Now it depends on both U and V. And then we have, you know, your favorite aggregation function and so on. The key building blocks, the message function, which takes the features of the two nodes and predicts the message vector. The aggregation function, which takes a multiset, a bag of values in your mailbox and aggregates them into a single vector. And finally, the update function, which takes the old features of that node and the updated mailbox and predicts how the node features should update. And hopefully this is clear. These psi and phi functions are the only parts where you have parameters. And once again, typically you'll take these guys to be your standard 1 or 2 layer neural networks with, you know, multiplications by matrices, ReLU functions, stuff like that. And you can train them with gradient descent because all of this is a differentiable function. Yeah? Okay. Now, it's a super generic layer, and I must stress that it has been independently discovered several times from different perspectives, and each perspective actually gives you a valuable new way of looking at things. So the original kind of term message passing neural networks came from the Justin Gilmer paper I showed you earlier today. They looked at it for analyzing density function theory outputs in computational chemistry. But in parallel, these kinds of equations were discovered by gated graph neural networks from UGelli and others, structured TVEC, which connected them to probabilistic graphical models. It's a pretty interesting area if you like Bayesian learning. Patchy-San from Matthias Niepert and others, and also interaction networks from Pete Battaglia and team, where actually they use them to model physics. So you can imagine, you know, these different messages. So you can imagine the nodes as like particles or planets. and you can imagine the messages as forces by which one particle acts on another particle, and this basically computes the aggregate force and tells you where should the particle move as a result of doing that. The Interaction Networks paper spotted this and made a use of these models to model n-body systems in physics. Yeah. I think Razvan was on this paper too, right? Yeah, cool. So this was a whirlwind tour, hopefully with some useful references on how to implement these models. Now I'm going to revisit that thing I told you that we're going to talk about towards the end, where we sort of just assume that the graph we were given is a good graph and we shouldn't touch it. So thus far, we always assume there exists a given ground truth input and that your GNN should not modify it. The adjacency matrix should always stay the same. However, I'll give you 3 examples for why this might not be a good idea. First of all, you might have cases where your graph is perfectly correct, but then it might not be a good idea to use that graph. Here is a simple motivating task. I have a graph with a bunch of nodes. Can you predict whether a pair of nodes is connected, whether there exists a path between them? I can easily be super adversarial and create this path graph where there's exactly like one edge in the middle that's missing. And your GNN now needs to make a linear number of steps before the features from one node will propagate to the other, so you can answer this question reliably. And this is not good. But for those of you coming from computer science, you might know I can reorganize these edges in a different way in a so-called disjoint set union data structure, which has much better complexity of how many layers you need. In fact, the inverse Ackermann function, which is constant for almost all values of n, near constant. But this is only in the case where the graph is perfectly correct. But in the real world, we don't have perfectly correct graphs. Even the molecules are just an approximation to the underlying physics. So this becomes really true when you start to model proteins, and AlphaFold did protein folding and is a very popular model for this stuff in computational biology. If you look at the actual molecular graph of a protein, it's a very linear molecule. It's like a polypeptide sequence. But then this sequence folds in 3-dimensional space, and suddenly things that are super far away in the molecular graph become super close in 3D space and interact a lot more. So if you did message passing just on the molecular graph, you would completely ignore this very useful proximity structure, right? So the graph is actually not perfectly correct, even though chemistry teaches us that it's perfectly correct in some other way, right? And also some graphs, even if they're perfect, even if they're correct, they're just pathologically bad. Specifically, you won't even be able to fit training data on graphs like this with a GNN. One classical example of a very bad graph is a graph which has a bottleneck. So imagine having these 2 cliques where everybody is completely connected to everybody else, and you have this one poor bottleneck edge connecting them. I hope you can see how this one edge is under a lot of representational pressure if it needs to carry the information across the 2 cliques very reliably. In fact, you can prove that in graphs like this, a GNN needs the number of features that exponentially grows with the size of the cliques in order to fit them perfectly. Even training data. I'm not even talking about test data. It can't even fit the training data. So it might be a good idea to rewire this graph, is basically what I'm saying. So how could we do this? Well, we could also just decide to do nothing and assume if we don't know a good graph, let's just not let anything be connected. A neighborhood is just the node itself. In fact, this gives rise to a very popular model, the deep sets model, where your message function is just applied on a single node and there's no aggregation and that's it, right? You could also decide to say, if I don't know the exact connections, let's just do it the lazy way, right? And let's assume everything is connected and let the model figure out by itself which pairs of nodes to connect. So now I've written down, say, the attentional GNN, where I'm doing aggregation over all of the nodes. Does this equation look familiar to any of you? Any models that look like this? Transformers, exactly. So this is what I was trying to tell you from the beginning. The transformer, which is the backbone of all modern large language models, you get the same equation by trying to do an attentional GNN over the complete graph. Or, well, specifically if you do GPT, because you need to worry about causality, you actually have a fully connected causal graph, so data cannot flow into the past. But still, there is a graph in there, and data flows between different words or parts of words and tokens by following pairwise interactions, and the dot product attention computes a soft adjacency matrix. You do inject some things about sequential information through the position embeddings, but the model itself doesn't have to use that information. Its main symmetry is permutation invariance. It's not a position invariance. In a way, you can think of these models, because they're built to ingest data at a very efficient rate, as GNNs that are currently winning the hardware lottery. because these kinds of operations work really well on modern GPUs and TPUs. I can't talk more about this connection. I don't have a lot of time, and I'm already running out of time. But Chaitanya Joshi wrote a really beautiful blog post in The Gradient called Transformers or Graph Neural Networks, where he dives deeply into the equations of these two models and lines them up to one another. Right? So if you want to read more in depth about this connection, this blog post is a wonderful place to start. So if no edges or all edges are two choices, obviously there's a choice in the middle. And that is to non-parametrically rewire the graph, which is, pick out some other edges to add to the model, where those edges are defined using some algorithm that only depends on the graph. So the reason why it's non-parametric is because there's no parameters in here. The model is not learning how to build these graphs. It just has an algorithm telling it how to do so. And you could also add parameters in this, so have a differentiable function that looks at your input graph and figures out what extra edges to add. This is called latent graph inference and is also another popular way of doing things. However, I would argue non-parametric rewiring hits a very particular sweet spot because it doesn't ignore all the information. It's a bit easier to scale because not everything is connected to everything, and it's easier to generalize with graph size. And the problem with this approach is that choosing an edge is a discrete decision, and you can't easily push a gradient through a discrete decision. So it's much easier and more scalable if you can find an algorithm to give you edges to use. Yeah? Now I'll quickly go through the 3 different ways in which you can put new edges in a graph this way. One, the graph diffusion convolution just says the graph itself is a great place to look for new edges, so just use something like PageRank to find new edges that shortcut your input graph. It's elegant, it's versatile, it's easy to use, but it kind of relies on a homophily assumption. It relies on things already being connected in the graph, sharing the same label. And then if you shortcut that, you'll have an even bigger wealth of information. And also it adds a bunch of new edges into the graph, which might drastically change your input statistics. Recognizing this, some folks from Michael Bronstein's group came up with this idea of looking at a graph as a discretization of a more complicated manifold, and then saying that the learning issues happen when there's a contraction in this manifold. So they search for edges that have very negative curvature, and then they try to insert extra edges around those bottlenecks. So now it's not changing the whole graph, it's more surgical around the critical areas. That preserves the input statistics, but this measure is local as well as highly expensive to compute. So it's not always super practical. And there's a third category of options, which I've also worked on together with Andrea Deac and others, which doesn't try to analyze the input graph at all. We just say, give me a graph which is good. I don't care if it's connected to the input graph at all, but just brutally use this graph. I know it's very good. I don't know if it's related to the problem, but I know it's excellent at globally propagating information. Such graphs in math are called expander graphs, by the way. And then just alternate 2 GNNs, one that runs over your original graph, one that runs over the expander. And you can see why expanders are really good. They have very small numbers of neighbors, but information can travel super fast in them. In fact, you can go from any node to any other node here in just 4 hops. They even, when you draw them like this, it even looks a little bit like the brain. So maybe the brain also internally built something expander-like where you have, hundreds of millions of neurons, but not so many connections per neuron. You have to be very efficient with how fast information travels. And I'll very quickly, I know I'm overrunning on time already, very quickly say how all this relates to LLMs, because I'm sure many of you want to also hear how this relates to chatbots and GPT and stuff like that. There'll also be a really cool tutorial from Federico, Ricardo, and Larissa where you'll deep dive and write code on top of LLMs. But let's just quickly, for the sake of this lecture, survey how large language models process data. So let's say you have a bit of text, a house of, and you want to do next token prediction on that, so predict the house of cards. You typically have 3 different types of layers. You have an embedding layer, which takes each word and embeds it in a high-dimensional space. You have a local feed-forward network, which takes each one of these node features and maps it in a higher dimensional space, but it's doing so for every token separately. And you have this attention layer, which, as we said, is causally masked. So every token sends information to all of the tokens in the future, and there's this kind of attentional style update that takes place there that allows the different words to interact. And then for every single token, you simultaneously predict the next one. And this allows you to very efficiently train on a lot of data. So actually, as you might expect, there's a graph here. So even though we often think of LLMs as sequence models, they're actually secretly graph models. And in fact, looking at them as graph models is a very good idea. And to show why it's a good idea, I'm going to show you why the graphs inside modern LLMs are actually quite bad for generalization. I'm going to do a bit of a question for the audience. So let's imagine we're going to look at a problem of just copying a single digit from our input, okay? And specifically, we're going to ask, say, a chatbot like Gemini, ChatGPT, or anything like this, what is the last digit of 111110? And then what is the first digit of 01111 and so on, right? So I want a show of hands. I want us to think which of these two do you think is more difficult for the language model? So raise your hand if you think it's easier to predict the last digit. And raise your hands if you think it's easier to predict the first digit. Okay, some of you have clearly read my papers, I guess. Because I would never have said this. Like I would have said last digit is much easier because as humans, we kind of remember the last thing a lot better than the first thing we heard. But yes, indeed, obviously models will always fail when you add a sufficient number of ones, but they will fail on the last digit way before they fail on the first digit. And the reason why this happens is, first of all, you have this congestion in the model where the final tokens embedding is what predicts the final output, and this is the computation graph of a transformer kind of directly overlaid. And I'll just skip this slide to show you that the reason why the early tokens are easier to predict than the later ones is just look at the graph. They have a lot more paths through which they can send data to this bottleneck compared to the other ones, right? So this final token actually has only one path to the end. So if that path gets cut in any way or overwhelmed, it's not going to be able to be usefully used. And as you add more data, the potential for overwhelming is much easier. In fact, in the limit, you can show if you were able to build an infinite layer large language model, it would only depend on the first token and all the other ones would just disappear. We have a few papers on this that we've done together with Federico and Alex and a bunch of other folks, Razvan as well. If you're interested to learn more why transformers need glasses and how to make a graph that's better than what's currently being used, I invite you to check out these two papers. If you want to get in on the action, there's a rich ecosystem of libraries for both PyTorch, TensorFlow, and JAX. I will share the slides so you can look at this later. There's lots of data sets you can use if you want to get in on the action. OGB, which is like the ImageNet for graphs, TU datasets, and benchmarking GNNs. And if you want to do some research in this space, talk to me after this, and I'd be happy to chat to you about it. The LOG conference is one of the premier venues where you can do this. Okay, thank you so much for bearing with me. Hvala vam. Let's stay connected.
Thank you, Petar.